Welcome back to part 2 of 2 for chapter 7. I don't know if you're binge watching these like a Netflix series, but if you just watch the previous one, we're going to roll right into the second one with 2 review problems, and then we'll cover the rest of chapter 7. So on page 4 of the notes in chapter 7, here is a multiple choice question. I'll show the choices in a second, but they are also in your notes book. What statement below best describes UV light, which has a lambda of about 250 times 10 to the negative 7 meters, as compared to radio waves, which in many cases have fairly long wavelengths. Here it's 0.25 meters, so that's like a foot. And so look through those statements and find the statement up there that is the one that best describes them. Or is there no statement that does that? And so I'll come back in a second with the answer. So please do a quick pause. Let's look through the choices one by one. First statement, it says UV rays travel via photons while radio waves use electrons. They both go by photons, so that's not true. UV light has less energy per photon because there's a shorter wavelength. The opposite would be true. They're very high energy. UV light moves slower. That's not true because they'll move at the same speed of light. And so then obviously UV light can't move faster. So this is a no statement is true. It's one of those situations you have to trust yourselves on the answer. And so the next question up there is for some group work. So maybe you have a parent around, or sometimes on Zoom I see people's pets running around, so maybe you can have your pet help you out on this, or a parent. For the 3 visible lines in the hydrogen spectrum shown, here they are. Which color has the longest wavelength? Which color has the highest frequency? And which one has the largest photon energy? So try to work through those after you hit pause, and then I will return with the answers. Hopefully the longest wavelength portion was easy. The longest wavelength up there would be the red because it has 656 nanometers. And so that is the red. The highest frequency is the highest energy and shortest wavelength. So that is the blue light at 434. Largest energy per photon is the same answer as B. The blue light has the highest energy. We're going to see where these lines come from in the next portion. But this is high energy stuff over here and low energy stuff over here. This one is just right. It's just in the middle. Maybe it's not too high energy, not too low. We call that Goldilocks. When we opened the chapter, we had looked at these ideas that people knew about flame tests and fireworks. This goes back to page 1. And then, for the hydrogen spectrum, if we go back a slide, the wavelengths of these lines, people had figured out that they fit this formula. That's how they calculated those wavelengths. But they had no idea where they came from. They had no idea what these numbers meant, but they knew that these small whole numbers worked in the formula. What we'll look at next is how Niels Bohr helped figure all this out and start quantum mechanics at the same time. And so when we look at a slice or kind of a cutaway of an atom here, this is the nucleus down below. These values where it says n equals 1, n equals 2, 3, 4, 5, these are effectively the rows of the periodic table. And so these are called, principal energy levels. And people had figured out soon before this that you could not be between energy levels. That energy was somehow what's called quantized. It's like when you walk up a flight of steps, you can only be on a step. You can't be between two steps because your foot would hit the steps, you fall down or something. And so electrons, as it turns out, and this is Bohr's series of postulates that help figure this out. We're going to see that electrons are going to be in those levels. And this is this quantization. And so he said that an electron could, in theory, be here. That would be sitting in level 4. Imagine going up some steps at your house. You can be on a step. You can't be in between steps. And so an electron could not be right there because it would be between levels. The lowest energy, as you can probably imagine, is level 1, and this is the perfect distance from the nucleus. And we're going to see that turns out to be basically the diameter of a 1s orbital. And so electrons can only be at very specific energy levels. That's the first part, and he did some mathematical calculations that showed that the energy of any level, where n here is only whole numbers, can't be 0, it's 1 to infinity, but it's whole numbers. And the energy is negative RH, and here is this constant called Rydberg's constant. It's 2.18 times 10 to the negative 18th joules, and then that's over n squared. And so when an electron is in energy level 1, then the energy is RH. If you jump up to level 2, then the energy has changed by 4 times because it's a squared function. And we'll use this as part of another formula in a little bit. And the other thing that Bohr had figured out, and I mentioned this a few minutes ago, is that these numbers, as it turns out, these are the row numbers on the periodic table. So n is 1, that's the first energy level. N is 2 is the second row of the periodic table, and etc. 3, 4, 5. And so that's why there's no 0, because there is no 0 energy level. The other thing that Bohr figured out is that if you have an electron in a specific energy level, let's say it's sitting there, level 4, an electron can jump to another level. If it wants to go from here to here, let's say, that will require energy. Think of it as going up steps. That requires energy. And so going this way, you would have to put in some energy. You can put it in the form of, could be a photon hitting that electron and making it jump up. It could be some electricity when you plug in a light bulb or something, or plug in a light. It could be the explosion from a firework. And so he realized that electrons can jump between levels. This process requires energy going up. When an electron spontaneously falls to a lower level, energy is released. So this thing sitting in energy level 5, that electron can fall, let's say down, I don't know, can go down to 2 or 1. Depending on quantum mechanics, there are different rules as to how they fall. That process releases energy. If this is happening inside a light bulb, then a photon comes out and you see the color. And so the energy is released in the form of a photon. So when that falls, then a photon comes out, which is usually shown as a wiggly line. the electron never leaves the atom. But like when a light bulb is plugged in, for instance, electrons are constantly being pumped up to higher levels by the electricity. And then when they fall back down, they're releasing photons. And then they hit your eyes or bounce off an object so you can see it. And so that's what's happening continuously. Like I said, in fireworks, when there's an explosion, the electrons are elevated to high energy levels. When they come back down, they put off different photons of different colors. And so that's why different elements produce different colors, because they all have different energy spaces. And so Bohr came up with a formula that we'll be using. I won't do the full derivation. I'm just really going to give you two equations to work with. And here are the two equations that will get you through the book problems. And we don't have to worry about the signs and how the full derivation came about, but basically I'll give you the start and then I'll give you the end. The change in energy is the final energy minus the initial energy. And as we saw on the previous slide, the energy of any given level is that negative RH over n squared. And so there's a quick sign change that has to do with endo and exothermic that we won't need to bother with in the derivation. But if you're given a problem that involves finding the change in energy when an electron falls from a high level to a low level, this will be the formula we'll be working with. It'll be that constant for hydrogen. That's the H on there. The 2.18 times 10 to the negative 18th joules. And then it's multiplied by NF squared. F is final, and so that's basically the energy level the electron ends up in. So F is final at this point. Minus 1 over n sub I squared, where in this case, the I is initial. And so this is where the electron starts, and we're going to where it ends up. So F is final. I is initial. And N is represented by the electron energy levels. So N has values of 1, 2, 3, 4, 5, etc. It's only whole numbers. And you'll see some book problems where they ask you for the wavelength. And there's just a slight variation on this formula. And so this is solving for the energy. And we saw in our previous video that the energy of a photon goes by the formula E equals hc over lambda. And so we'll derive that quickly. So since we know E equals hc over lambda, we can just change that out, fix it that lambda. H and C are actually constants we're going to put in the formula, and algebraically I'm going to divide each side by H over C. Back too far. And so what will happen is the HC's will cancel out. And formula 1 over lambda equals RH over HC. RH and H and C are all constants. If we put all of those in a calculator, Okay, this is 2.18 times 10 to the negative 18. H is the 6.63 times 10 to the negative 34th joules times seconds. C is the speed of light, 3 times 10 to the 8th. And so if you put all of those in a calculator, you get 1.097 times 10 to the 7th per meter. And so you get the formula that people had figured out for these energy levels of hydrogen. It turns out they didn't know what the numbers 2, 3, 4, 5 meant, but it turns out these were energy levels that electrons were jumping in between in hydrogen. And so when the electrons were coming back down, they were emitting these photons of light. And so people, like I said earlier, had gotten this formula just strictly by trial and error. And so Niels Bohr derived it, what you'd call from first principles. He came up with the same formula, and he knew what the terms meant. So you'll see some book problems where they're going to ask you for the wavelength. Use this formula. The answer will come out in meters. If you're asked for the energy, then I would use the one from a minute ago, where it's just delta E equals RH times the energy level difference. Keep in mind, these values are squared. And here's a practice problem for you to try. This is on page 296 of the textbook. It's in the notes booklet. What wavelength of light is emitted when an electron falls from the 4 level down to the 2? And so we're just using that formula where you solve for 1 over wavelength. Be careful on this, because when you do it, you're solving for 1 over the wavelength. And so you're going to have to flip your answer. So pause the video and we will return with the solution. Here's our formula, and we want to put in the final energy level, so this is 1 over 2 squared, because that's where it ends up, minus 1 over 4 squared, because that's where it started, its initial. And when we do the algebra on that, you end up at this spot. As I mentioned a minute ago, you're solving for 1 over the wavelength. And so in order to get the lambda, on your calculator, you have to invert that number. And so the wavelength in meters is 4.86 times 10 to the negative 7 meters. If I wanted to switch that to nanometers, I would multiply by 1 billion, because nano is to the 9th. So in a different unit, this is 486 nanometers. And that number is one of those visible photons of light that come out of a hydrogen atom when you excite it with electricity. And you see up top here, there is the 486. I should probably change the color of that here. Kind of something bluish greenish. And so add that electron transition to the atom in the spectrum. And so what's happening in this situation, I'll do this one, you can try the next one. There's an electron sitting in level 4. Okay? The electron falls to level 2. It's still in the atom, but it falls. When it does that, some energy is released. And so you usually do photons as squiggly lines. And so then what happens is there's the photon that comes out. And it's a photon of 486 nanometers. It's the fall from 4 to 2. Okay, you can check your math on this if you wanted to. But try to use your logic skills to add the transitions from 5 to 2 and 3 to 2. Obviously, they're one of these on the left or the right. But thinking about the amount of energy in these transitions and the size of these transitions, basically the question is the 3 to 2 transition this line or this line? Think about it for a moment, and then I'll come back with the answer. I'm going to change the color here. So I'm back on the red pen, and so this would be the red photon. That is low energy, so that's only the fall from 3 to 2. And so you can imagine an electron sitting right here. It falls down to level 2. It will emit a red photon. Make it a little more squiggly. Like a little wave of photons. And so there's my red photon coming out. The 5 to 2 is the biggest drop on these. So we can imagine an electron, even though they're not purple, just stick with that color. It falls from 5 down to 2 and puts out that purple photon. And so that produces that spectrum, because that's the biggest gap. You can check the math easily on that, but those are the values you would get. One small quirk, the book says 657. I don't know if they're doing a rounding difference, but I get 656 when I do the red. So don't worry about your math. You get 1 nanometer off. Here's your figure from the textbook that shows what's happening. There's your 3 to 2 transition, red photon, 4 to 2, greenish blue photon, 5 to 2, purplish photon. And as we'll see in the next example, there are lines in the UV range. We just can't see them with our eyes. So there are other lines, but these are just the ones you can see with the human eye. So now that you're nearing the end of Chem 2, your math skills, I think, have improved greatly since Chem 1. And so why don't you try this problem, where you have an electron falling from a certain level down to another level, then you're given the wavelength of emission. And so why don't you try that, and we'll come back and talk about the solution. I can work through it. Well, the setup in the original algebra is the same as our previous one. 1 over lambda equals the constant. So there's our setup. This time we have the lambdas, 9.5 times 10 to the minus 8 meters. Constant over here. We know it ends up at level 1, so that's 1 over 1 squared. The unknown is n sub I squared, the initial level squared. So that's our setup, and then we need to do the algebra to finish that. And I would recommend starting off with just dividing this out on your calculator. So 1 divided by 9.5 times 10 to the negative 8th. If you divide that out, you get 1.053 times 10 to the 7th. And the units right now are per meter. Then we can bring the constant over here because we're effectively dividing each side by the constant. If you want to see all the algebra, we'll put the constant down here. That will go away. So we divide both of those out. They're both the same exponent. They're almost 1. They're not quite 1. And so when we divide that out, you get 0.96. Two constants all over here. Algebraically, then this is 1. And so we ended up with 0.96 equals 1 minus 1 over n sub I squared. So there's our algebra at this point. We subtract 1 from each side. Sorry about that. You end up with negative 0.04 equals negative 1 over n sub I squared. So algebraically, we can make both of these negative signs go away, so they're both positive. And then we have to algebraically invert both sides. So we got to flip that side, we get n sub I squared. On your calculator, flip that. You end up with 25. Take the radical of that. We only want the positive root. And so in this answer, this question, the answer is n sub I. The initial level is 5. An electron has fallen from 5 to 1 and emitted a photon of that wavelength, which turns out to be 95 nanometers if we convert the units. And so if you look at that scale on 267, 95 nanometers would be down in the ultraviolet range. And so when you excite some hydrogen atoms, those photons of 95 nanometers are coming out. We just can't see them. And so the three lines we did earlier were the visible lines, but the UV lines are there. But we just can't see them because those are bigger and larger transitions. Here's an at-home problem to try. Maybe you can, I don't know, grab a sibling or something and see if they can do this. Which line here, I color-coded mine, which line corresponds to the largest quantum leap? And then we'll do the second part after that. So we look at these 4 lines. The largest quantum leap would be the blue line at 460. Because that's the photon with the greatest energy. Part 2 of this. If the orange line at 610 is a 5 to 3 transition, which line up there is the 6 to 3? And effectively, we can rule out the blue line because we're looking at, is it the one on this side of 610, the greenish line at 492, or is it that reddish line at 672? And so when we're looking for this transition, we see that it's a bigger gap. And so we must have a photon coming out with more energy. And so the 6 to 3 line must be that greenish line at 492. The reddish line has to be a smaller transition. It's very likely it's probably a 4 to 3 transition. But we know a bigger transition is a shorter wavelength, higher energy. Here's a summary of the Bohr model, and this will also tell us about some of the shortcomings of it and talk about quantum mechanics and electron configurations. So Bohr correctly predicted energy levels and quantum leaps. There's no doubt about it. He's the person that really came up with this idea, and he was right. The model explained many known phenomena, things like flame tests. He explained those line spectra. Fireworks were explained, how they worked. In a sense, this could have predicted things like laser beams and other products like that. So this explained many things. It turns out the model, though, was less accurate for atoms larger than hydrogen. And we'll explore why that's true in the next slide or two. And this led to the details of electron configurations. We know now about things like S and P orbitals, but we'll see Niels Bohr at the time did not know about those, and he was involved with the people who figured all that out later. So here's the first thing that Bohr did not know at the time, but he learned later from some other people, is that electrons, and it turns out everything, travels in waves. And so if we look at this diagram over here, you can see the nucleus in the center. In some ways, the Bohr model thought of an electron going around in a concentric circle. It was really spherical, but in a sense it was going around in a perfect circle. That's why they called those orbits. And sometimes the Bohr model is called the planetary model. But it turns out electrons are actually traveling in waves. This is the real behavior of an electron. It's going in waves. And so, just like a photon, that's a particle in a wave, an electron is a particle that travels like a wave. The book has some details in section, I think it's 7.4. But I would recommend just going on YouTube and typing in Dr. Quantum double slit, and you'll see some very strange things about electron behavior in about a 5-minute cartoon about the double slit experiment. And hopefully it'll get you thinking deeply about stuff in the universe, things you think you know. The second piece that came up was Heisenberg's uncertainty principle. It basically says that you cannot know the position and the velocity of an object simultaneously. There's some built-in error, and the more precisely you determine one, the more error you're going to have in the other one. And so that's the uncertainty principle, and it basically states that you cannot determine the exact place an electron will be. You can only determine the probability of it being somewhere. And an electron before quantum mechanics was thought of like this, called a classical trajectory. It turns out for electrons, this is not true based on the scale and the size of atoms. And so this classical trajectory turned out to be not true inside an atom. In reality, it looks more like this, where you have electrons going across a path, and all you can determine is a probability distribution map. And we'll see in a moment, instead of having electrons in orbits, electrons will be in orbitals of probability. If you look, we'll see what a baseball player sees. And so the key here is that the exact path cannot be determined. You can only figure out the probability of a path. And so imagine yourself on the other end of this electron, and someone is slinging electrons at you like baseballs if you're a baseball player, and the catcher has a target up, but there's only a certain probability it will land in a certain area. The larger area you look at, the greater the probability will be. So here, for example, there's a 70% chance it'll be in this outer circle. If you went to 90%, you would expand the range. And so the further out you go, the greater probability you have. And these are really going to be what orbitals are, where you put electrons in areas of high probability. The other thing Bohr didn't know, and in some ways he got some bad luck on this, because it turns out electrons have energy sublevels, and we know them now as SP E, D, and F. But in the case of hydrogen, it actually doesn't have energy sublevels based on reasons that go beyond this class. But in hydrogen, for instance, the first energy level just looks like this, as we know, 1s. And so in hydrogen, you only have one electron, right? And that could be that half arrow we used back in Chem 1. You notice the 2s and the 2p are the same level. So when Bohr would have an electron jump up to here by providing some energy, you move it up there, and then it falls back down, you send out a photon. Hydrogen was very simple, because the 2s and the 2p were all at the same energy. But it turns out in elements basically other than hydrogen, elements larger than hydrogen, now the 1s, there's the 2s, and the 2p is at a different energy level. So what happened with the model was that the spectra were more complicated than he thought, because larger elements were getting different kinds of leaps. You could take an electron, move it up here, or you could move it up here. And so these spectra were more complicated. The model couldn't quite handle it. And so people knew there was something going on here, something different. And this is where these fine-tuned electron configurations came up. So in some ways, like we said earlier, the Bohr model is this planetary model. Here are the electrons flowing around. If you count up the yellow dots on there, you'll get 11 electrons. So this is sodium. In the quantum mechanical model, it looks more like this, where it's very roughly spherical, but we know we have a nucleus in the center, and then we have the 1s and 2s. We're going to actually watch a very short video clip that I hope shows up well on YouTube. It's actually a different YouTube clip that I downloaded, and it's going to actually show how the orbitals kind of get built up, and it's going to be in neon, so it'll only go out to element 10, and then of course sodium has a little bit more than that, but it'll be a very short video. And so you can see here that the nucleus will be in the center where all the lines converge. And then we bring in the 1s orbital. As we know from our previous experience, the 1s is spherical. So you can imagine in that 1s orbital, you can put 2 electrons. There's a 2s, it's larger. Now when the 2p's start coming in, that's the 2px. And so 2 electrons could be in that 2p orbital. There's a 2py coming in. And so once again, you can put 2 electrons in that 2py orbital. There's a third orientation for our dumbbells, for the p's. So this is called the 2pz because it's 3-dimensional. And you can put 2 electrons in there. And then, so this would be the equivalent of neon if it was full. And it can hold a total of 10 electrons in there. And so that's why atoms are roughly spherical, even though it's not strictly spherical, but we kind of treat atoms as a rough sphere. So like I said, that would be the equivalent of the first 10 electrons. Sodium just adds that third layer. You can see out here there's the 3s orbital in there. So for some practice, what is the electron configuration of sodium? So as we're filling these, we would get a 1s2 as we know, 2s2, and then even though there are 3 2p orbitals, we usually just treat them all as one set. And so we would say 2p6 because they're filled. You could write, some people might even write them out separately, like 2px2, 2py2, 2pz, but we'll treat them as a big set, 2p6. That's the equivalent of neon, and then we grab the sodium, gives us that 11th electron, and so there's the electron configuration of sodium. And Bohr, like I said, was treating these a little bit differently. This 3s1 right here, in the Bohr model, is that electron right there. But in the Bohr model, they would have just put 7 more electrons in that third level, and then potentially even 10 more, if you count the 3Ds, but they weren't considering sublevels. And so it turned out it was just a little more complicated than they thought. And so here is some good practice for part 2 of chapter 7. And then stick around though, because the next slide has the extra credit problem. And so once again, we've got some multiple choices on page 293. There are 3 problems there. And then there are some problems that involve orbitals here, and then some math problems involving the Bohr model. And then there are a couple of problems here. This is actually from chapter 8. If you don't have a textbook, drop me a line and I'll send you this, because this involves some electron configuration practice, which might show up on the chapter 7 on my quiz exam on Blackboard. And so if you don't have a book, let me know, I will send you these problems. But these are in chapter 8, they're on electron configurations. And so this is good practice. And here comes the extra credit. And so this is due by Monday the 20th. Time-wise, just get it in by midnight on the 20th. And you can send me, the best way for me is to send me a picture of your work. And so fill in the table here on the number of protons, electrons, and neutrons in these isotopes, if you want to call them that. That's an ion there, sodium +1. And then fill in this spot here. And so fill in all the blanks on this. Got that spot, fill in that, and then those spots. And then write the complete electron configuration of the ion in the last row. So whatever you put in here, write out its complete total electron configuration. So whatever goes in that slot. And before you do it, you can even check your answer with me. For some of the folks that did the extra credit via Zoom, that's another easy way to do it, because we just do it together, and then you don't need to send me anything. And so it's a chance to get some free points. So it's due by Monday the 20th, and then we will probably have the quiz for this probably a few days after that. We'll leave you a nice open window, and then we'll get into chapter 19 after that. So if you have any questions, send me an email, or I'll see you on Zoom.